we're going to learn about S and R squared today. S is the standard deviation of the residuals, which means it's giving you the typical prediction error. In other words, if you look at the graph and you find a residual, which is the distance from the point to the graph, this is going to be how far off your points typically are from that prediction line. Okay? The formula is the square root of the residuals squared, the sum of all of them, divided by n minus 2. So you would find every single residual, so every single actual minus predicted, and you square it, and you add them all up, and you divide by n minus 2. N is the number of points that we used, and you square root it. So we talked about the truck problem. And if you took every single residual, you added them all up, you get that ginormous number, 461,300,000, okay? And you divide by 14 because we had 16 trucks, and you square root it, you get $5,740 for your typical how far off the points are from the mean, okay? So here's the sentence that you're going to write. This is more important than the formula, all right? If we use this model to predict the values of the response variable, so that's your y, from the explanatory variable, that's your x, our predictions will typically be off by about s units. So if we were to put this in the context of the truck problem, if we use this model to predict, what are we predicting in the truck problem, you guys? Yep, its value, or the price of the truck, okay? So if we use this model to predict the price of the truck from, what was the x in the truck problem? It was mileage, okay? From mileage, our predictions will typically be off by about, whatever that number was that we just said, $5,740, okay? So the formula is given to you, but typically so is the standard deviation. So you don't have to actually calculate it. Same with the r squared. You just really need to be able to interpret it, okay? But I do want you to write the formulas down just in case. All right, so that's standard deviation, your typical distance that you are away from the line. Now we have r squared. So you guys have seen r squared on your calculator. It is actually r squared, right? So we talked about r. R tells you the closer it is to 1, the more linear it is, as long as you look at your data. So this is called the coefficient of determination. You do need to memorize that. I would write that down, what it actually is, the coefficient of determination. That's just the name of it. We'll talk about how to interpret it and how the heck they find it. Okay, so back to the truck problem. How can we predict y if we don't know x? Suppose that we randomly selected an additional used Ford F-150 that was on sale. What should we predict for its price? So we've got the figure, shows the scatter plot of the truck data that we studied throughout the section, including the least squares regression line. And we added another horizontal line that is the mean of all the y values. So basically, they took the average of all the prices. Okay, so they add them all up, divide by 16, and they drew this line right here. This is called y bar, which is the mean of all the prices of the trucks. Okay. If we don't know the number of miles driven for some truck that we're going to try to buy, then we can't use the regression line to make a prediction. And so our best guess is to use the mean price of all the other trucks that we know, which is kind of weird, all right? But if we don't know the mileage, We can just take the average of those 16 trucks, and our best guess is that it's $27,834, which is where they put that line. Okay, so how much better does the regression line do at predicting prices than just using the average price of all of those trucks? So here we have our average price and all of our 16 dots, and notice all of our squares. That's basically taking the distance and squaring it, and then they're adding them all up, okay? This is what we were doing yesterday with our regression line, and notice those squares are smaller, right? Because it's a better prediction line than just the average. Hopefully it would be better, right? Otherwise we would just use the average all the time. So the squares are much smaller here. This is better. So how much better? That's what R squared has to do with. How much better is it to use the regression line than just the average? So the ratio of these two quantities tells us what proportion of the total variation is in Y still remains after using the regression line to predict the values of the response variable. So let's try it in this problem. So we're going to find the sum of all the residuals, which is what we just did. So we have the sum of every single data point minus the predicted point, which is what the regression line gives us. And the problem just told us that the sum of the squares was this really big number, okay? And we're finding the proportion of this compared to if we just took the data point minus the mean squared, if we didn't have that line, okay? The data point minus the mean. And that number happens to be, in this problem, 1,374,000 million, just kidding, okay? So this number is way smaller, and it should be, because we were just talking about the sum of the squares being smaller. All those squares were smaller. So what is this decimal? 0.336, okay? This is what is unaccounted for. This is the variation that's unaccounted for in the picture. What we want is what's accounted for, and so the formula we use is 1 minus that percentage. So it's the same formula except 1 minus that lovely decimal. So the coefficient of determination is the fraction of the variation and the values of y that's accounted for by the least squares regression line of y on x. So how much better does the regression line do at making a prediction when we just compare to that line in the middle, the mean? I would write this down, okay, but then we'll write the lovely sentence, which is what you really need to know, because r squared will probably be given to you. Or r. And if they give you r, can you find r squared? Yes. And if they give you r squared, can you find r? Yes. Okay. They go together. All right, so here's the sentence that you want to know for r squared. So blank percent of the variation, and what you're going to plug in here is the actual r squared that you get, which is typically given to you, in, and this would be your y, or your response variable, is accounted for by the linear model, meaning that y equals mx plus b line that we found, relating your response variable to your explanatory variable. So if we're doing the truck problem, we would say 66%, because 1 minus that 33%, 66% of the variation in, what was our y variable, you guys? Price of the truck, right? Is accounted for by the linear model relating the price of the truck to the mileage of the truck. This is one of those sentences you kind of just have to memorize, and it's not as like intuitive probably as some of the other ones. So hopefully you guys wrote that down. Great. Let's try some problems where they give it to you and we can just interpret them. So back to our football problem. We looked at the relationship between average points scored per game and the number of wins for the 12 college football teams in the SEC. A scatter plot with the least squares regression line and the residual plot is shown. The equation is given to us right here, and they give us S, which is what? Standard deviation, and they give us R squared, which is called what? Coefficient of determination. Great. Okay, so part A, calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. So the residual, you guys, that's what we talked about yesterday. Residual is always equal to actual minus predicted with the y values. Some of you guys use the x values, by the way. Y values. Talking about y's, all right? So actual would be 11 wins. Predicted, we have to find from the equation. We plug in our 30.1 into our equation, which was y hat equals negative 3.75 plus 0.437, and we plug in 30.1 for points scored, and that gives us a predicted value of 9.4 wins. All right, so our actual was 11. They actually won 11 games, but our predicted based on the line is 9.4, and we subtract, and we get 1.6. It does say to interpret it, you guys. So basically, South Carolina won 1.6 more games than expected based on that prediction line. Okay? All right, part B. Is a linear model appropriate? We talked about this yesterday. Based on these two graphs, who can tell me which graph we're going to look at and if a linear model is appropriate? We learned how to find this on our calculator. Anybody? Ivan, what do you think? Very good. This is called the residual plot. There's no leftover pattern, and so a linear model is appropriate. Okay. Also, this looks fairly linear over here, but use your residual plot. All right, interpret the value of S. So here's what we just learned, how to interpret these. So S is 1.24. We're talking about points per game and wins. So who can fill in this lovely sentence for me and tell me how to interpret S in the context of this problem? And S is 1.24. Olivia, what do you think? You guys want to help her out? Wins. Points per game. What, you guys? Wins. We're always talking about the y value here because it's how far you are away from the line and the y distance. Okay? Cool. All right, and then we're going to predict r squared in this problem. So let's go back to r squared is 0.88. All right. Anyone want to do this one? Mitch, what do you think? There you go. Okay. All right. That was all that. Cool. So you guys have to be able to interpret regression output. This is really hard to read, so I'm just going to go to the next one and we'll talk about it. This is a little clearer. So you're going to be given this lovely output quite often, which you can say thank you because then you don't have to do all the calculations, okay? So they give it to you, but you have to be able to read it. So right where it says constant directly across, this is always your y-intercept. Okay, so that's always on top here. And across from whatever you're talking about in the problem is the slope. Another way to remember it is it goes A, B, as long as you write your equation as A plus BX, which is how we memorized it. So A goes first, B goes second, A is your y-intercept, and B is your slope. Okay? The other thing they're giving you is this S. What do you guys think that is? Standard deviation. And R squared is your coefficient of determination. Okay? We don't need anything else yet. We will talk about a lot more of them as we go through the class. But right now, all you need is y-intercept, slope, standard deviation, and R squared. So they give us the output. What's the equation of the least squares regression line that describes the relationship between foot length and height? Define any variables you use. So we would say y hat equals, what's our y-intercept? Yeah, 103.41 plus, what's our slope that I just X'd out there? There we go. 2.7469 times x, and then you would need to say what x and y are. So what are we talking about? We've got foot length and height, and so we're using foot length to predict height. So x is foot length, y is height. Interpret the slope in the regression line context. So here's our slope. This is the sentence for slope. So you would say for every 1 centimeter increase in foot length, the height in centimeters increases by 2.7469. Okay, that's your slope thing. Find correlation. This is important if you've zoned out. Make sure you're paying attention. R squared is 48.6%, right? How would you find R? Square root it. And what you want to do is make it a decimal, 0.486. And then you're going to square root R squared in order to find R, which gives us 0.697. And again, R, you guys, means there is a moderate positive linear correlation between foot length and height. Okay? And then is the line an appropriate model to use for the data? Same thing we were talking about before. Is there a pattern to the residual plot, you guys? No. So should we use a line?